Welcome to Advanced Data Analysis 1 with me, Erik Erhardt, Professor of Statistics at the University of New Mexico. In this video, we'll be continuing with Class 27, the two-way categorical tables and simple linear regression. In the last video, we covered the two-way categorical tables, and in this video, we will cover the simple linear regression. So in this assignment, you will need two numeric variables. You have created plots of two numeric variables in previous assignments and calculated their correlation and so on. Those variables are probably good choices to use here. So we do not have a markdown file here. This is part of your project. If we just bring this over to our studio, this is where we continued last time. This is the outline file. In fact, maybe just very quickly, a good place to start will be in the outline file that you have. I'll scroll down to Class 27 and we'll look at the rubric for simple linear regression. So choose two numeric variables, and it's nice if your numeric variables have a nice range with lots of intermediate values. I'm going to show an example in this video which is sort of on the edge of not being great. So you do want to try to choose something at least as good as the ones that I've chosen, perhaps better. So we'll start by plotting the data, and if necessary, you may need to transform some of the variables so that you have roughly a linear relationship. In a previous assignment, we looked at doing logistic transformations, logarithmic transformations on variables when we have observed curvature, and those transformations sometimes improved both the spread of our data as well as the taking curvature out of our data. Once you've plotted the data and are satisfied that you've got something that's roughly linear, then we'll do all of our interpretations based on that transformed scale. If you're lucky, no transformation will be necessary. Next, fit the simple linear regression model. No points for that because all the action is in assessing it and interpreting. So we need to first, we're going to check for model fit first. So do the residuals show any evidence of lack of fit? That is, we've got structure in the residuals, non-constant variance, lots of things can happen there. Checking for normality using QQ-plot, assessing if we have points that have undue influence on the fit of the regression. And if we're happy with how the residuals look, then we can continue. If we don't like how the residuals look, we may need to perform some action that improves the model fit. That might mean going back and doing transformations. It might mean removing a point or two that are extremely influential in your data set. But once we're happy with all that, then we will assess whether the slope is not equal to 0, and also interpret the R-squared value. That is the assignment for today. All right, so I'm going to open up RStudio and I'm going to knit the document. And while this is knitting, I'm going to take this portion of the rubric and copy it below into, I'm paging down, into the section for simple linear regression. And I'm going to tidy this up a bit and make these parts of the assignment subsections. Excuse me, I could not think and push the buttons at the same time. Okay, so now we've got some place to put each part. So the first thing is to select two numeric variables. Now I'm going to wait for this to finish because I want to go back to my correlation plot to see if there's a better example for me to use other than one that I used in a previous year. Oh, I guess I can probably do that right away because we have a fairly current one up here. Let me look at my correlation assignment. Okay, well this one finished. We can look at the current one. I'm just looking for the correlation methods. Correlation, correlation, correlation. So it looks like I looked at age and total cigarettes smoked. Let me scroll down and see if I did any other ones. That's it. I'm not crazy about using age as a numeric variable, so I think I will choose a different one. Let me look also at the numeric variables. Scatter plot and see what I did down here. Here I show height versus weight. This is the type of relationship you would love to have, but we don't really have data in our assignment. So I also have age and cigarettes smoked. Okay, so I don't love that example. I'm going to go with the one that I have previously used in a previous year. Okay, so I went to my HTML file here in this red, and I'm scrolling down to the, sorry, it keeps pausing on me, my browser. There we go, simple linear regression. Well, I clicked on it and it's not jumping. Let me press F5. That should reposition my cursor to this heading, simple linear regression, right here. There we go. Okay, I just need to be patient. Okay, so this analysis is using days smoke. So how many days per month do you smoke? And I made this numeric variable out of a categorical variable, and then I'm plotting the total number of cigarettes that the person smokes per month. So how many days per month you smoke related to the total number of cigarettes you smoke. Now certainly, the more days you smoke, the more opportunities you have to smoke cigarettes. So we should expect an increasing relationship here. Let's make sure that we go and understand these variables, since I believe these are variables that I created out of other variables. So days smoke and total cigarettes smoked. So I'm going to jump up to the top and go down to my codebook. And I think this is under my created variables. Here is days smoked and total cigarettes smoked. So the first one, days smoked, is based on smoking frequency. So let's go up and see that categorical variable for smoking frequency. Here it is, smoking frequency. And so from these categories, every day down to once a month, I created numeric values. And we can take a quick look at days smoke. Have I? Well, you know what? Maybe this is actually days smoke. Okay. So I have a typo in here. So here's how I created that variable. If someone smoked every day, meaning they were in category 1, then we gave them a value of 30. If someone smoked 5 to 6 times a day, category 2, then we made 5 to 6 was 5.5. We assume that there was just 4 weeks in a month. So 4 times 5.5 is 22, and so on. And so we have a set of numbers here, which is days smoke. So that's going to be our x variable. Next, let's look at the y variable. Total cigarettes smoked. So this is based on the days smoked, which is what we just looked at, and times the daily cigarettes smoked. So let me scroll up a little bit to, let me scroll up a lot because we weren't actually up at the code book. Hang in there for a second. Where's my code book? Alright, sorry. Daily cig smoked. That's what we're looking for. Daily cig smoked. Okay, so this is when someone smokes cigarettes, how many do you smoke? Now, I'm assuming, there is an assumption in this variable name that usual quantity when smoked cigarettes, that I'm assuming that this is on a daily basis and not in a one sitting basis, right? For example, you could have breakfast and then smoke 3 cigarettes and then have a pause in your day, eat lunch, and then smoke 4 cigarettes, right? And in that case, the usual quantity would be like 3 or 4. But over the course of the day, we've had 3, we've had 4, maybe you have 4 more at night. And so then you've had 11 in a day. So I have made an assumption here that this is actually the number of cigarettes you have in it one day. Anyway, so that is the variable I'm using. I'm paging down, and that is going to be total cigarettes smoked. So it is a function of our x variable. So it should increase, and it probably should increase linearly too. Okay, so anyway, we've got those 2 variables. That's what we're going to work with. If I press F5, will it jump me down to the simple linear regression area? I think it should. There we go. All right, and so now we're ready to get started. I do notice that I've got a linear model here where I'm actually have done the square root transformation. I'm going to start with the original scale and then see if I need to make any changes. The data set that I used in a previous year is subsetted to only young adults from 18 to 25 years old, but this year I've used everyone in the data set. So relationships could change. All right, with all of that background, it's quite a bit, let me grab this so that I can search in the R Markdown file. And jump right there. And I'm going to start by copying a bunch of code into my R Markdown file, and then I'll come back and then I'll start working in the R Markdown file exclusively. So the plotting of the data, I'm just going to say see below. I sort of like that idea because the plot of the data may also include the fit of the linear regression, including confidence bands and prediction bands, things like that. Those are not required for your plot, but let's see. Then we've got assessing model assumptions. These are better performed, not with this code, but with what I'll show you in a moment. In the previous assignment for simple linear regression, we used a function that I wrote from the ADA functions for model assessments. It is here, these LM diag plots. So that's what I want in my R Markdown file for the assessing the residuals. Control-Alt-I creates a new code chunk, and LM fit is my object name, and that's going into my diagnostic plot. Okay, so everything's looking good so far. Go back over here to the code. I'll copy this text in case that's the interpretation. At least gives me some language to start an interpretation. We assess normality. I'll copy this in case we have a similar interpretation. Assess the relative influence of points. Okay. So I'm going to grab this stuff. It actually looks like I redo the analysis because I had influential points. So we'll come back and look at that in a moment. I've got a hypothesis test here where I print out the summary and I state my hypotheses and interpret the conclusion of that hypothesis test. And then I've got the R-squared interpretation. Okay, so now I've got everything I need to get started with this assignment. And I know I could save you guys a lot of time watching this video by preparing this beforehand. However, I think that it's valuable for you to see the process that I'm going through. Even if I'm going sort of quickly, anyway, I think that there's some value there. So I'm going to copy my previous code and change this to the original variable name. I'm also going to make a correction here because we just noticed that I had a typo for day smoke. It should be days smoke. So I'm going to search wherever it was day smoke, singular. I'm going to find that and replace that with the plural. Was it really just one place? Seems like there was more, but anyway, there we go. Okay, so I just want to get back down to linear regression. Okay, so I'm going to say see below on the plotting of the data. And let's fit our linear regression. I'm also printing out the coefficients. I'm going to make my, well, I guess I don't need my console that much bigger. I was looking for errors. Let's see if all this produces a plot without errors. Aha, so I'm not using my square root variable yet. In fact, I haven't even created that variable in this project file. Okay, this window is going to be too small. It also is going to take a little while to produce these plots because there's 40,000 points. And it's plotting every single one of them. Okay, but we can sort of get an idea here that we have, looks like we've got some right skewness in each of the groups, right? Most of the data is sort of down low, and then we have these points that sort of stream off to the top. Let me do one more thing. When I plot the points, instead of the alpha being 0.7, let's make it be I want it to be really small, 0.05, so we get a sense of the density of these points. Geom jitter, I don't know, it's fine. Okay, let's make our plot window a little bit large. Oh, I should have cleared my plot window first, so that it doesn't need to try to redraw all those points when I resize this. Okay. Once this goes away, I'm going to rerun the plot. Because I really want to get a sense of the distribution within each of these days smoke values. I think that we're going to get a high density of people who don't smoke that many cigarettes, and then it's going to trail off. That suggests to me that we need some sort of transformation of the y variable, something that removes that right skewness. So maybe that means taking the logarithm. Maybe it means taking the square root. In fact, one of the things we can do is we can look at the diagnostic plots to give us some information as to what transformation would be most valuable. Okay, so yeah, I'm seeing high density of points down low with a few observations in the upper tail. So we clearly need to transform the y variable. Let's use the diagnostic plots to help us choose what to do. It is using R base graphics, so it should go a bit faster. Let's make this plot window a little bit larger. I do hate how it changes where you are in the editor window when you do that. Okay, you can really see that sort of right skewness in these plots, these residual plots. Let's go back one screen in the plots by clicking this left arrow over here. Now it's taking a while, possibly because my computer's a little slow, but also because we have such a large sample size. Okay, so here's our QQ plot. If our data were normal, they would fall along this blue line. And we're not seeing that. We see this sort of upward curvature. In fact, the middle of the data seem to follow the normal distribution, that blue line, pretty well. But in both tails, it's pretty bad. And so this upward curvature is indicative of right skewness. So we need to take some transformation of the y variable. Cook's distance. Anyway, once we know that we don't have normal residuals, Cook's distance and leverage are not that informative. If we go to the next window, there we go. So there's a sixth plot here that's not being shown, which is the a plot for the Box-Cox transformation. That's a suggestion for what power should we raise the y variable to in order to help our data be the most normal. And that one didn't show up probably because maybe our data set is too large. So I'm going to try one more thing. I'm going to clear the plots, and I'm just going to run the diagnostic plots one more time. If it doesn't come out this time, then I may show you how to run it manually and see if we can get just that plot. Okay, so it didn't come out this time either. If we look in the LM diag plots code, the last command here is for the oh, no, those are added variable plots, excuse me. We want to do the Box-Cox plot. Okay, I've got a bunch of switches. It's in the car package. In fact, sometimes I think this is a plot that sometimes gives an error. And yeah, here we go. So Box-Cox. So yeah, so if it gives an error, I sort of don't create this plot. But let's try this command right here. Okay, so this is a bit of magic, but we have a LM fit. And if I press enter, first argument must be strictly positive. So I think we have values that are negative. Let me try changing the lambda from 0. Let's see if that makes a difference. Nope. Okay. So I think we're not going to be able to get that plot to help us make a decision about transformation. So what can we do? We've got data that are clearly right skewed. And in fact, the variance also increases as x increases. Now, I think in Chapter 8 of the lecture notes I show what to do when you have non-constant variance, as we have here. I think I'll probably ignore that for this assignment. So first thing we need to do is take some transformation of the y variable. So let's go back into our source file over here. And I think, let's see what variables I already have for the y variable. So we've got nisarc_sub, we've got total cigarettes smoked, and I have a log2 version of this. Let's try that as my y variable. That logarithm will improve the skewness, meaning it will reduce the skewness. Let me clear my plots out. Heck, that's not so bad in terms of skewness, right? We have a lot of symmetry in each of these groups. I like that quite a bit better. In particular, I like it for the largest group, right? Most of the observations are people who smoke every day. But it seems to work pretty well for the others too. There's a little bit of a right tail. You can see sort of the dark points sort of clustered in the middle bottom, and then there's a few outliers in the upper bands, but not that many. I think this is much better. And the line does not really follow the center of the data very well. And so we may actually need also to take the logarithm of days smoke to draw this tail in. So it may turn out that a log-log transformation is the way to go. I'm quite sure that I do not have a log version of days smoke. But if I think I can just do log of this base equals 2. Let's see what happens if we it may give some error for so we definitely have the log 2 of the x-axis here. I'm going to ignore these bands on there. The blue line is correct, and the cluster of points is correct. I think logging both axes in terms of the blue line following the centers of the black points, I think that's pretty good. So what I'm going to do is I'm going to create a new variable, which is the log 2 of days smoke, up in the area where we need that variable. And then I'll use it for this analysis. So if I search for _log2, I found the area where I created that new variable for total cigarettes smoked. So let's do the same thing for days smoke. I've got my log2 up there. In fact, I'm just going to create it here, I think. And there is a function called log2 in R, and that will create that variable. Now, because I'm sort of working in the console and I know how to be careful, I'm going to run just a single line from here by selecting those lines to run. Here, let me come down here and clear my console. I'm going to select those lines to run. I'm going to skip these other lines which have run previously already, and then close the parenthesis. And that now gives me a nisarc sub that has the log2 variable, because I ran basically just this one line. So now I've got a log2 version of days smoke. All right, let's go down. I wish I had remembered the line number I was on. Am I getting closer? Okay, so let's put in here log2. And in my plot, instead of doing this log manually, I'll put in the variable that we created. I'll run the linear model code. I'll run this plot. Interesting. I've got it up here. Okay, let me look at that error one more time. This object not found. Okay, let me see if there's. Oh, there is a this lm fit command. It needs the correct variable name in the predict function. So I think that that's going to correct that error. So if you do change the x variable, you need to also change the x variable for the ribbon. Okay. You know, I don't love it. It's not perfect, but for this assignment, this is pretty good. I'm happy with this. Okay, and I think I've done a better job than I did in the previous year. Well, I'm not necessarily going to say that. I'm looking at different data because I'm looking at all people. Okay, so I like this. We've got the log. We needed the log scale to have a good plot. It's a good thing we did that section on the logarithm. Now, do recall, right, that in fact I'm just removing the jitter for a moment. I just want to remind you that this horizontal jitter is artificial. It doesn't affect how the model is being fit. The diagonal regression line in there and the confidence bands are based on the actual data values. The only reason we've put some jitter in there is to help distinguish the points that lay on top of each other. If you think that there's a little too much jitter, you can reduce the amount of jitter in the plot. Okay. All right, so we fit this model now on the log scale. Let's look at the diagnostic plots and assess the model for lack of fit. All right, so we'll go back to the first plot. We may need to resize these windows. I'll probably just zoom. Oh, these are ugly. So this is tough, guys. So our data clearly are not normal. At least, the residuals. Residuals clearly are not normal. We have a huge sample, 43,000. The error bands on normality get extremely narrow in this case, and it's quite easy to find observations that deviate from normality. Furthermore, the data acts a bit like a step function, right? You see these horizontal lines. That's because I'm using a variable that I created out of a categorical variable, and those categories force us to have only certain numeric values, and so we end up with this step. So one point of evidence here is the QQ plot suggests that we don't have normal data. Now the plot itself, I don't know. I won't say too much, but it suggests that we don't have normal data. Let's also look at a few other sources of evidence. The problem is we have such a large data set. We have a lot of sensitivity and statistical power to detect small deviations from normality. So we want to maybe take a little more holistic view when we've got such a large data set. When we look at the Cook's distances, of course, we've got lots of data points that are way down low, but we don't have any single values that are super influential, and that's partly because we have 43,000 observations. So you would need a single value that is outrageously big to have much influence over the remaining 43,000 values. In this case, I would say is not so bad. when we look at influence on the vertical axis, when I say influence, Cook's distance is a measure of influence. As a function of leverage, it's those values that have high leverage that also have high Cook's distance. So it's because they are outliers in the x direction where they have influence. So very, very low days smoke along the x-axis, or very, very high days smoke along the x-axis. Let's go to the next page of plots. All right, so we're looking to see that the residuals are centered about 0 and don't have any strong structure. Now, it's a bit tougher to see the density of the points with this plot because both of our variables are constructed out of categorical variables or functions of categorical variables. They have discrete values, and so there's any one of these points could actually represent 1,000 points. So it's really hard to see the density. One thing that we see is that the regression line, which is effectively represented by this horizontal line at 0, it seems to underestimate people who are predicted, that means the fitted value, people who are predicted to smoke very little, and it basically estimates accurately those who smoke the most. The reason that is because most of the people smoke every day. So we have most of the evidence over here, so the regression line is really going to cater to that, and it sort of gets worse for the groups of people who smoke rarely. And the pattern we see is similar between the fitted values and the x variables days smoked log 2, because the days smoked variable, because we have a positive correlation between the x and y variables. So you'll see the same pattern. Given the size of our data, I would say that we're not doing too badly. We're definitely going to predict people who smoke a lot much better than our predictions for the people who smoke very little. Let's see if we can see those same patterns in the plot of the data. Yes, we can. So when the days smoked is very high, the regression line goes through the middle of the cloud of data. But for these people who smoke very little, the regression line is coming down near the bottom. So most of the points are above the line. And even that's not quite right. It's not that most points are above the line. In fact, let's change the alpha level of these points to be very, very light. Because what's happening is that almost everyone is down here near 0. I think that's the problem. So there are some people who smoke once a day or once a month, and when they smoke, they only smoke one cigarette. That's this dot at 0. These are the people, because we took the logarithm, the log of the value 1, log of 1 equals 0. That happened in both axes. And so these are people who smoke 1 day a month, and when they smoke one cigarette. Okay? And there's a whole bunch of them. Look how dark that spot is relative to the rest of them. And so that dark spot is dragging the regression line down towards it. That has a lot of leverage, basically. So, I don't know, this seems like this seems like a decent representation to me of the data. There are some deficiencies in the residuals, and we'll make some comments on that right now. Okay, so I'm going to undo or get rid of the previous interpretation, and let's go over here. So basically, we want to step through each plot. QQ plot. Pattern is non-normal. After the log 2 transformation, So initially, so I'll say on original scale, the pattern is non-normal with right skewness in the y variable. After log transformation of both variables, we still do not have normality, but it is much better. Right, you'll recall last time on the original QQ plot we had a horizontal blue line, and then we had an upward curve with the black dots. Now at least our black dots are buddies with the blue line, so that's pretty good. All right, let's see what else. We've got the Cook's distance. Here we see, several points with slightly higher influence, but none with extremely large influence. So then we also have the Cook's distance versus leverage. In this plot, in here, we see that those values with the largest Cook's distance also have large leverage. Those points with high influence also have high leverage. Thus, it are those points. Thus, those points that are extremes in the x direction have the highest influence, and the points that are extremes in the x direction are the least frequent or most frequent smokers, those who smoke the most days. We go on to the next plots. These are just the residual plots versus, and I'll just do the residuals versus the x variable, the second plot, since they are the same. They'll also basically be the same if you had a negative correlation, except the x-axis for fitted values would be reversed in that case. All right, so I'm going to focus on this one. We've got the main problem here is that the single dot in the on the left side bottom of this plot, this represents hundreds of points, but you just don't get that nuance in this base graphic plot. So each group of values, each group based on the x variable, right? So this variable, we've got these 1, 2, 3, 4, 5, 6 groups. Each of those group of values is, roughly symmetric. And the zero line, I guess this is like the y equals 0 line, passes through the center of most groups. The x equals 0 group has many values or many observations at the lowest value, which is why the regression line, or this zero horizontal line, is so close to the bottom there, which is why the zero code line or regression line is below the the distribution that is spread above it. Okay. So, assess the residuals for normality. So I sort of discussed that above. And assess the relative influence of points. So maybe I should bring some of these interpretations down here. Assess the residuals. So this is about the residual plots up here. Okay, so the residual plots, that can stay up here. Then I do normality. That's these QQ plots. There we go. And then I've got influence, which is the Cook's distance. And I'll bring that down to the influence. Okay, so I just took my bullet points and I distributed them in the sections that followed it. I'm not going to go through all this code that I had from the previous assignment because I don't think it really applies. All right, so what do we do now? We have made some discussion about the diagnostics. The diagnostics indicate that the model fit is not perfect. Furthermore, it's unlikely that we can do any transformations to either the x or the y variable to improve this relationship beyond what we've done. This, I think, is going to be as good as we get. We've created two numeric variables out of categorical variables. There just isn't a way to get a perfect straight line relationship with symmetry, normality symmetry over the regression line. What would you do? In practice, you might think about fitting another type of model that's beyond the scope of this class. There's ways of doing non-parametric regression, but actually, I would probably be somewhat satisfied with this regression model for this data in practice. So, in your assignment, regardless of what you've concluded, as long as you've done your best with transformations and maybe removing one or two outliers to get a model, or rather to get a data set that a linear regression can fit well, if you've done your best and it looks pretty good, maybe just admit that. So I'll just say up here that though the model assumptions are not perfectly met, we will continue to interpret the model that we have. Okay, so go ahead and move forward. So I'm going to print out the summary of the model. Let's make this a little bit bigger down here. We have, now keep in mind everything's on the log 2 scale. Our coefficients here, we have an intercept of about 0.5 and a slope of 1.6. And this p-value is the p-value for testing whether the slope of total cigarettes log 2 scale related to days smoked on the log 2 scale, whether this slope is statistically different from 0. That's the null hypothesis. Is this slope equal to 0? We see this positive slope here. It's quite positive, actually. So there's quite a bit of evidence to say that it is not equal to 0. You know what? I don't have my confidence bands on my regression line. I think I probably have up here, I probably have standard error equals false under smooth. Oh no, it is equal to true. Holy moly. I know what's happening. Let me zoom in on this plot. So let me look at it on my full screen for a second. There is a tiny gray line around the blue line. I'm not sure if you can see that, but we have so many data points that the confidence band is extremely narrow. So that's what happens when you have too much data. It's not a bad thing, it's just the situation we're in. Okay. Okay, anyway, so we've taken a look at this. We also have the multiple r squared value down here, 0.7. This is remarkably high, right? So r squared is the square of the correlation coefficient. So if we look at the square root of 0.7373, we have a positive correlation here of 0.85. That's very high. And it's largely, I think, because we have got a large set of points down in the bottom left corner. We have a large set of points in the upper right hand corner, and that's and we don't have that much spread after having taken the logarithm. Anyway, I think this is quite a nice model for the data that we have. I'm happy with the log transformation. Okay, let's go down to our conclusions. The rubric is asking us to test whether the slope is different from 0. So the alternative hypothesis is that beta 1 is not equal to 0. So cool, we get a different conclusion when we look at everyone. So we saw in our table that our p-value was very, very small, basically 0. Therefore, we're going to reject the null hypothesis that the slope is equal to 0 in favor of the alternative that the slope is different from 0, and in fact it's quite positive. So let's go over there, and in fact let's do a couple more things. So in this summary, if I look at the names in the summary, there is a coefficients table. Okay. So summary of LMFIT $ coefficients. That gives us this table. That's the same, right? This line here is the same as this line here at the bottom. Okay. This is a table. It's got 2 rows and 4 columns. So if I want the p-value over here, it's going to be the second row and the 4th column. That's the p-value. The estimate is going to be the second row, 1st column. That's this one here. So we can grab those values automatically and put them into our result. So I'll say, because the p-value equals, and I think I can put this in $ and do double a left tick r space and the coefficients, and I'm going to pipe that to signif 3 for 3 significant digits. Because the p-value equals that, which is less than 0.5, we reject H0, the null hypothesis, in favor of the alternative. I think, am I using HA or H1? I forget. In favor of the alternative, concluding that the slope is different from 0. Okay. And I also have an interpretation of the slope. I do not ask you to do that, but I will provide that. Furthermore, for every additional, okay, maybe better not to. So the interpretation is extra. For every increase in log 2 of days smoked, for every unit increase in log 2 days smoked, we expect an increase of this coefficient down here, 1.6, we expect an increase of that much to 3 significant digits in the log 2 of total cigs smoked. Okay. I have a previous comment that on the original scale, this increase is scary. And I think that still holds. The more days you smoke, the more total cigarettes you smoke, and this is a log-log scale. And I think we did, the first thing we did in this video is we plotted the data on the original scale, and it was scary. So let's just for our own curiosity, go back to that just to see how dangerous is it if you smoke every day relative to just on the weekend. Oh boy. Okay, paste it down here. Let me give myself some space to work. I'm just taking out the log 2 suffix of each variable name. Okay, this was the original scale. Basically, you stayed down pretty low until you become an everyday smoker, and then you smoke a lot. All right, so let me refit my linear model and print out the summary one more time so that we've got our R-squared value right here. Okay, so we've got this summary. Let's look at those names one more time. We've got an R-squared object right there. So summary lmfit $sign R-squared is that value. What a interesting number. Let's see, R-squared equals that number, and I think 3 decimal places is plenty. The R-squared is that. The R-squared is the proportion of variance explained by the regression model of, y versus x over and above. I don't know why I say over and above. Maybe just above. Over. Over using the grand mean of y alone. Okay, and if you want, you can replace the names. Okay, what did I have before? The regression model explains that much proportion of variance in the response over using the mean value alone. Okay, I didn't need to retype that. I think either of those is just fine. All right, and that is the end of the assignment. I know I was sort of jumping around a lot in this assignment, but I think I hope that this video is helpful for you to complete it. There are a few other resources available to you if you find yourself getting stuck at this. Of course, there's a ton of office hours with either myself or the other TAs or peer learning facilitators. You can look at examples of linear regressions from the lecture notes. You can look at the version of this assignment from the previous year on the website. right here in the red area. Right, you can click there. So yes, so get the help that you need for this assignment. Let me just make sure, so I've created this plot, but I think we want to resize the window for this plot. We also want to do a couple other things for this plot. We should probably label what the bands are in a caption. I think a height of 6 is probably fine, width of 8 is good. Let's go down to here where the labels are. Caption. So blue band is regression line. /n gives a new line. And we could put a period at the end of our sentence. Blue band is the regression line. You can't see it, but the gray bands, actually I'll say blue line, that's better, is the fitted regression line. The gray bands, the gray band is the confidence band, new line, and the green band is the prediction band. Now we never looked at the prediction band in this assignment, but anyway, I sort of think it's a nice annotation. Okay, so now we've got a caption in the bottom right. I like that quite a bit. So I will knit this and give it a minute to take a look at the result and see if we need to tweak anything. It probably would be good to improve the labels on the X and Y axis. Maybe I'll go and do that while this is compiling. So we've got a title, we've got a caption. I think usually I like to put the X and the Y labels before the caption. So X is log 2 of day's smoke, and log 2 of total okay. I'm not going to recompile just to look at those axis labels. So I know it's taking a long time, partly because we've got some plots, some previous plots, which have these scatter plots with lots and lots of points in it. While this is working, let me go find a plot like that and disable it so it doesn't take quite so long every time. Here we have this ANOVA. This rug might be taking a long time. Anyway, let's open this in the browser and look at the current assignment. Simple linear regression. All right, so I looked below for the plot. We fit the linear regression. I don't know why I put out the coefficients. This is the intercept and the slope, but okay. I do note that the prediction interval should be bounded below at 0 rather than having predictions that are negative down here. If you wanted to be better, you could change these prediction values. In fact, it's not too hard. You take this value, and if it's negative, set it equal to 0. So an if-else statement could fix that pretty easily. Anyway, this plot looks pretty good. It's got those captions. We assess the residuals. These residual plots are maybe a little bit tall. It's not so bad, but I might set the, here we go. We might set the size of this as well. Oh, right, I'm miles away because I was doing something else. Here's geom points from a previous plot. I'm going to disable that one. I disabled it, right? The easiest way to disable a piece of code is to go after the initial triple tick and move the brace R to the next line. That treats it as a verbatim block. You can still read the code in the assignment, but it doesn't create the plot. The other thing that can sometimes take a long time, especially with these histograms, are the rugs. So you can remove the rug out of there. Here's something where I'm plotting points. Okay, I'll remove that. All right, so if your computer is super fast, you don't need to do this, but this computer that I'm using is almost 10 years old. Okay, I think that's good enough. There was one more geom rug that I wanted to disable. I got that one already. Here it is. Okay, the thing I was about to do was, in the simple linear regression for the diagnostic plots, put in the height and the width, and I think a width of 8 and a height of 3 ends up being pretty good. We can do a double check on that. Now this should compile a bit faster because I've removed some of those plotting commands that took a long time. In particular, there was one that was like code chunk 70 or something that took a long time. Oh, here's one, code chunk 27. Of course, it's unnamed code chunk 27. But it is where there's a geom smooth. So I can search through those. Here's, oh, that's the one at the very end. Ah, here's one. Oh, that's the current one. Maybe that's a stat smooth. Okay, it's probably this one for the correlation. Yeah, that makes sense. So stat smooth was creating a plot that here's another one. Oh, height and weight. Okay, I'll comment that one out. Okay, looks like I've commented out basically all of the scatter plot matrices. So we were going to look at these residual plots. There we go. Oh, those look a little bit better. The boxes are a bit square. Sorry, it jumps around as it's loading. I think, okay, so yeah, 8 inches wide, 3 inches tall. It's basically sizing a row of 3 plots. Now it's cutting off the rightmost title on this one. It doesn't really matter. Okay, that looks pretty good. We've got our interpretations for each of these in here. I use HA, okay, and my p-value is numerically indistinguishable from 0 to a computer, and it looks like one thing that didn't work was my number wasn't appearing down here for my slope, and I think that is probably because I left out an R inside those single braces. Let's try to find it. Here. The regression model explains. Okay. Interpretation. Oh, this is the slope. Okay. Go up to the slope. Yes, there it is. So I want this piece of code to run, but I need to tell it what language to run in. So I need an R space. Okay, now it will compute that as a number. And then finally, R squared disappears as a number. Okay, so we've tidied this up. I'll just knit it one more time to get this R, but I think we're done with the video. Hope this has helped you with this assignment.